Having completed the various methods in terms of generalized estimating equations, or more generally as they're sometimes called semi-parametric methods, we are now in a position to apply them to the toenail data set. All five, well, not really all five, we will do the first one, Liang and Ziegler 1986. We will do the linearization-based method, and we will do alternating logistic regression. All right. So the model is still the same. Very briefly, we have a straight line at the logit scale for the standard arm, which corresponds to capital T equal to 0. A straight line for the experimental arm, which corresponds to capital T equal to 1. And we want to know whether beta 3 is equal to 0, yes or no. If it isn't, if we reject that hypothesis, we conclude that there will be a treatment effect, and hopefully beneficially, in the sense that in the standard arm, the evolution is a bit slower than in the experimental arm. Okay, basic GEE. There are two procedures available for us in SAS, ProgGenMod and ProgGEE. I will not mention ProgGEE right now because it does essentially do the same things as ProgGenMod for us here and now, except when it comes to missing data. Then there are differences, and we will discuss it dutifully without any problem in the missing data part of the course. So, we have here onychomycosis response as a function of new treatment. Treatment by time interaction. The intercept is for free. Distribution is binomial, and we use the default link function, the logit link. The repeated statement is very important, of course, because the repeated statement changes the ordinary logistic regression into generalized estimating equation. I could ask the question, what does repeated do in SAS? The answer is, you don't know until I tell you what procedure I'm talking about. Because, for example, repeated in mixed is for serial correlation. Repeated in GLM is for repeated measures ANOVA. Repeated here is for GEE and for alternating logistic regression. So repeated with, of course, the subject variable specified here, the subject option, which tells you all the lines corresponding to the same ID number is the same person. That's really what we want to happen. Within subject is time class. That's the ordering of the measurements within a subject, which is important when there are missing data. So if you have the first, the third, the fifth measurement, but not the others, SAS should not think that it's the first, the second, and the third. No, it should properly be the first, the third, and the fifth. So this is why you get the option to specify the within subject. But when it really comes to GEE, the key thing is type. Type is exchangeable, assumes all correlations to be equal. Type is UN, assumes unstructured, and so on. So COV-B is the variance-covariance matrix, and CORE-W is the working correlation structure that you would like to see. Model SE is the model-based standard errors, in other words, the naive standard errors. You do get the robust standard errors for free, but the naive standard errors, you have to ask for them. Okay, and then we look at the output. And I've selected a bit of output, and what we see here, if we look at the output immediately, is, for the treatment by time interaction, so beta 3, the confidence interval excludes 0, so it looks like we have a significant effect, but we should be very careful. These are the initial parameter estimates. Remember, we have beta initial. From there, using logistic regression, that's important, standard logistic regression. From there, we derive beta GEE, which are the final estimates. And then from there we calculate the naive or the robust standard errors. This is only initial, so it's the result based on logistic regression, which is valid only, if you assume that the measurements are properly independent of each other, which is not the case. Okay. Then we go on and we say, okay, fine, let's be careful. We have the second set of panels. We have the robust panel with empirical standard errors, and we have the model-based panel or naive panel with the naive standard errors. In both panels, do we get the same estimates for the parameters? And of course, that's not a coincidence. Never say, oh, that's a real strange coincidence in this example. No, it's always the case. You start from the same parameter estimates, as I've indicated a few times, and then you calculate the robust and the naive standard errors, respectively. Okay. Standard errors are different, and they're actually quite a bit bigger in the empirical case, insofar that you get a non-significant result robust and a significant result naive. And it's not just sitting on the border. They're actually both relatively far away from the border. So here you go. I'm giving you this result, and you show the 3 panels to the doctor. The doctor might say, hey, what is that? 2 of the panels have a significant result, but you tell me I shouldn't use them. I shouldn't use naive, especially not when naive and robust are so different from each other. The initial estimates are not valid, so what is it now? Well, what we seem to see here is that the exchangeable assumption is not necessarily the most efficient one. It may not be true, and we may be losing efficiency here, indeed. The working correlation is estimated to be 0.42, but watch out. 2 warnings. It's not part of the full formal inference. It's a working assumption. It's a correction that you apply to your logistic regression. It's not there. It's not good for interpretation. That's one observation. Another observation is we would like to understand why is happening what is happening with the standard errors. And to explain that, let me use the intercept. Well, the standard error for the intercept in the initial estimates is 0.11. So initial 0.11. Naive, we go next to naive here, it's 0.13. Huh? And then 0.17 robust. Well, initial means the initial estimate would be valid if the data were independent. But if the data are independent, you say 400 subjects measured 7 times, that's 2,800 data pieces. So it produces a standard error of 0.11, fine. Naive. Naive says the working assumption is right, but you do allow for correlation, and that correlation here is constant, 0.42. Now just imagine the correlation would be 1. If the correlation is 1, then the 7 repeated measures of the same subject really come down to the same thing. There is no difference between them. They all say the same. So yeah, you have 2,800 data points, but not independent. It really comes down only to 400. So a positive correlation for something like an intercept shrinks the information and therefore increases the standard error. That's what you see happen. And then we say, and further, the robustification, the correction, in other words, the sandwich estimator also comes with a check. You have to pay the bill, you have to pay a price, and that price is increased standard error here also. Right. With that in mind, how do we do alternating logistic regression? Well, very simple. You go back to the same code. You take out the word type is exchangeable, and you replace that with type is, and that is, in this case, going to be logor is equal to exchangeable. So type is replaced by logor is. In exchangeable is incidentally both in GEE with type as well as in ALR with logod's the same. But look at the manual and you will see that for various other structures it's a different name. For example, you have unstructured in GEE and you have full clust, which is the same thing, but then in the ALR context, which is all odds ratios are different from each other. Remember, the odds ratio is the one technique which is not omnibus. I cannot apply it to all settings. It is for binary data. It is with logit link and with the odds ratio as measure of association. And so an unspecified, fully unstructured odds ratio structure, we call that full clust. But there will be examples later on. The output is the same in structure, and so I'm presenting here naive and robust. Yeah, it's slightly more precise. The treatment effect here, it's slightly more precise, but I wouldn't call it greatly improved in those terms. What we do see in addition here is the alpha parameter. So the alpha parameter is the log odds ratio. And we do see in the empirical panel that there is a significant association in this case. And then the linearization-based method. The linearization-based method, I think nowadays we could say that can easily be fitted with the Glimix procedure. It's a byproduct of the Glimix procedure. GEE was explicitly implemented, but Glimix for marginal models, that's actually not an accident, but it's a side effect of a procedure that really is intended for mixed models. But we're not there with mixed models. The Glimix macro was written earlier, and it's interesting to see what it really does. Remember, what we do here is we derive a working variate, and that working variate is based on a Taylor series expansion. Now, to calculate a Taylor series expansion, you need to know its logistic regression so that you can calculate the derivatives, etc. And yes, the outer shell of the Glimix macro does specify exactly that information. It's logit for binomial data. If you say Poisson with log-link, it knows it has to calculate a different derivative. But then once you have that, you fit a mixed model for beta, and that mixed model core is given at the middle of the macro. And you see it's the same thing as anywhere else. Model, onychomycosis response treatment, time treatment by time interaction. Repeated subject is ID number, time class, type is compound symmetry. You get the point. And the empirical option here makes sure that you get robust standard errors. Should you want a naive standard errors, run it again, but with the empirical option removed. It means with GE, one call gives me both, and with Glimix, I need to have two calls. Yes, indeed, but before we go too much into how to use it now, today, then it's better to look at the Glimix procedure, because it came later, but it's much more flexible. It's easier to get it to converge, etc. So nowadays, I would not even use the Glimix macro anymore. It's very similar in syntax to proc mixed, except this very funny thing. Random underscore residual underscore. It's not a random effects model. And I repeat, it's not a random effects model. This is a marginal model. If it would be a random effects model, there would be something like random intercept. But if you say random underscore residual underscore, it is a marginal model. I honestly think it could have been called repeated, but no, it's not called repeated. So, subject is ID number, type is compound symmetry, all of that remains the same, and you get your output then. And I've summarized here on this slide what I've just said a moment ago. Watch out for the random underscore residual underscore. Okay, we're nearing the end of the chapter, but we still need to discuss the summary table here, and there are several things to say. First, the blocks, the rows, the big row blocks. This is method number 1, this is method number 5, this is method number 3. In other words, Liang and Ziegler, 1986. Number 5 is alternating logistic regression, but you see that here as well. And number 3 is the linearization-based method with Glimix. Okay, why is this empty? Well, alternating logistic regression or GE1 under independence, the odds ratio or the log odds ratio is 0 when the correlation is 0. That doesn't make any difference, so you can just as well copy that. Here, it's a different matter. There was a lack of convergence in that case. So it tells us that alternating logistic regression, because it uses odds ratios, is a little bit more difficult to get to converge than would be the case with alternating logistic, than with GE1. Fine. Next, if I take an arbitrary panel, you get your 4 parameter estimates, beta 0, 1, 2, 3. Point estimate, and then what we sometimes call jokingly, the law of generalized estimating equations says present the standard errors separated by semicolon within parentheses with the naive and the robust next to each other. Well, that's of course ridiculous. I think if you present a report for a medical doctor or another client, present 1 standard error. Where else would you present 2 standard errors? Well, Liang and Ziegler did it in their original paper, and everybody has been doing it since. But I really think it doesn't make too much sense to do that always, except like in this case, in a textbook or in the classroom. What we do see also is the GE1 panel and the linearization-based panel are remarkably similar, and that's what you would expect. They're really two different estimation methods for otherwise the same model. The model is the same. I have a logistic regression which is corrected for correlation. Only in the first case, I estimated by plugging in this working correlation directly into the equation. In the second case, I update the model via a tailorized version of the model. That's the difference. So here is the same. Under exchangeability, it's very similar, and some people say, yeah, but for unstructured it's different. It's very different because 720, and I'm looking here, and 630 are different. And not only that, 72 and 36 are very different. One is double the other. So how can you say they're the same? Well, I can say that if I look at the standard error. So in view of the standard error, there really is not that much of a difference. Next, if you look left, in the left column, you will see, and also to some extent in the exchangeable column, that the naive and the robust standard error are fairly different. Not always, but usually they're fairly different. And that gap shortens, that gap gets much smaller with unstructured. In some cases, they're even the same. And you would say, yeah, that's what I expect. Well, to the extent that I always expect it to be the same, because what is my logic now? Well, and think about it. If I say unstructured, it means the most general structure I can think of. So there could be no misspecification left with unstructured. But the robust standard error is a correction for the misspecification that is left, and I'm saying there is no left. So I have shown that the two sets of standard error should be identical, but they are not. I've made a mistake. I've made a logical mistake in my reasoning. What is it? Well, the answer is as follows. Unstructured in what? Because you always have to see what fully unstructured really means. So if I have a data set with 400 subjects split over 2 arms, 200, 200, and 7 repeated measures, true, unstructured means 21 correlations. Yeah, so it's unstructured in time. But what about capital T, treatment? That's the catch. Really, it's perfectly possible that there is a correlation matrix for arm A and a different one for arm B. Very likely that's the case to some extent. So, if I would allow that, the two sets of standard errors, if at all possible, will come even closer. They may not be perfectly the same because there are subtle issues with missing data. Because of missing data, it's still not entirely true. But if you would have complete data, no missingness, so a balanced design means everybody is measured at the same time, no measurements at the same times, same 7 times, no measurements are missing. Well, in that case, you would have, with an unstructured matrix with 42 correlations, a set for treatment arm A, a set for treatment arm B, then they would have become identical. So is this a problem that we cannot get there? Don't talk about those things in general terms. It might be, but it might be that it's not the case. And it's not the case because the two sets of standard errors are so close to each other that I wouldn't worry in the slightest. I know why it's happening now, but I think the magnitude of it, and that's what counts, is really not very importantly different. Okay, so if we now put the key elements next to each other, we see what we already knew. The working correlation structure version. So the robust standard, the robust p-value under exchangeability was non-significant. It would be worse under independence, but with unstructured we get a significant result. So this is a case in point where, yeah, all the point estimates are relatively similar throughout, and that's what we would expect. They're all consistent. The robust standard errors are all not so very different, and that is because the independence working correlation structure, while producing an invalid naive estimate, produces a valid robust estimate. But if they're valid, I would expect them all to be reasonably similar, right? The robust ones, I mean. But there is a gain of efficiency, and that's what we see happen here. So while they're all valid, there is some value still in having a sufficiently general working correlation structure, because it gives you a better chance of finding something that is there to be found. Yeah, but if you do unstructured, you have 21 nuisance parameters. Under exchangeability, only 1. Under independence, 0. So aren't you wasting degrees of freedom? No, I'm not wasting degrees of freedom. I'm spending degrees of freedom, and I need them to be spent because otherwise I misspecify my model. General wisdom, but of course there are always exceptions, is in a case like this, with 2,800 data points, give and take a bit of missingness, you have a lot of data. 21 nuisance parameters. If that really improves the fit of the model, really is a small price to pay for increased efficiency. So there's a lot more to be said about generalized estimating equations, but it is a nice, simple to use, maybe not necessarily so simple to understand all the details of how it works, but essentially it's a correlation logistic regression, simple to use in practice, simple to program, and fast, and also simple to interpret the results. But you need to have the right perspective on the working correlation structure. Okay, good. So that is essentially the end of this chapter. Not only that, it brings me to the end of the part on conditional and marginal models, and in the third part we will move towards hierarchical models.